So thanks for the organization of the workshop. Thanks for inviting me. And yeah, so today I'll start with like a very simple problem that is essentially like a very special case, but will give us all the ideas of the general case. And in the second part of this lecture, I'll just show how this can be like massively generalized. But if you understand this first part, you'll understand kind of everything you need to do like for the general case. Okay? So, okay, here's our motivating problem. I have a non-negative matrix A. I'm going to say that this is like a square matrix, and right, the entries are non-negative reals. And I'm just going to say that the norm for non-negative matrices is just the sum of all the entries. Okay, it's just the L1 norm. And then I'll say that A is doubly stochastic if all the rows and columns, they have the same sum. But by sum here, I'm just going to normalize them because I won't care if like if I take a matrix and I multiply all the entries by 2, if it still has the same row sums and column sums, it should be the same. So I'm just going to normalize the row and sums. Okay, so the row and column sums are going to be normalized. So what is the ith row sum of A? It's just the sum of all the entries in the ith row divided by the norm. Okay, and same for the column. And again, A is doubly stochastic if these normalized rows and columns, they all sum to 1 over n. Right, so here's 2 examples of doubly stochastic matrices, right? And you can see that if I multiply them by any constant, then they're still doubly stochastic by this definition. Questions? Yeah, so the norm, as I said, is just the L1 norm here. I'm just taking the, yeah. Yeah, but this will change in the second lecture, and I'll tell you when it changes. Okay? So, okay. Now, there's an important operation here that I can take a matrix A, and I can say, you know what, I'm going to do this operation. I'm going to scale every row. I can choose a scalar, and for every row, I can scale that row by one scalar, let's say xi, and every column, I can scale by another scalar xj, yj. So this gives me the transformation, like my matrix A is like aij. I'm going to scale like the ith row by xi and the jth column by yj. Right? So if I write this like in matrix format, like just for the 2 by 2 matrix, right, this x1 scales the first row, this x2 scales the second row, y1 scales the first column, y2 scales the second column. Does that make sense? So when I do this multiplication here, I get exactly my scaled matrix. Does that make sense? Okay. And okay, a very natural question, right, is like, okay, can I scale A? So if I give you a matrix A that's not doubly stochastic, my question is, can I scale this matrix to a doubly stochastic matrix? Okay? Okay, but now exact scalability may be problematic, right? Especially if you care about like numerics, right? So for example, here's one problem. Even if the input is rational, the scaling that takes you to doubly stochastic may not be. So here's an example. Like I give you 1, 1, 1, 2. The scaling to doubly stochastic, as you can see, like you can do this calculation, right, is going to be 2 minus root 2, square root 2 minus 1, square root 2 minus 1, 2 minus square root 2. So you cannot write this down, right, with enough precision. Like that. It's just not rational. Okay? But this is a mild problem. The other problem that we have, right, is that some matrices are morally scalable. Like if I give you this matrix here, like 1, 1, 0, 1, right? Clearly, if I multiply by epsilon and 1 over epsilon here, by 1 over epsilon and epsilon here, right? What am I doing? Well, my first row, I'm multiplying by epsilon, but the first column, I'm dividing by epsilon. So I preserve the diagonal elements, right? This guy is 0, so I don't care. It would always stay 0. But this guy here, I send it to epsilon squared, right? So this guy gets pretty close to doubly stochastic.
So your last 2 examples are sort of implicitly assuming this answer is essentially unique to trivialities.
That's a very good question, right? So we're gonna get to that in the second lecture, but not right now. But yeah, in the first one, we can definitely prove that that is the only scaling that you can get. Sorry, yes.
I know, but I'm just saying
yes.
In your lecture, you're assuming this is true without stating it.
Yeah, because I want to do a gentle introduction, right? Then all of this will be answered in due time. But you're definitely right. And I can come back to that, like to the reason why that one is unique. Why that is a problem. The first example is indeed a problem. There's no other scaling, right? You could ask. There's no other scaling. And for those of you who want to know the answers, like strong convexity, that will be the, okay? So yeah, but this one, like, right, we all agree that this should be considered scalable, and it's kind of, right, on the purpose of inclusivity, we should include this guy, like, as a scalable. So then, let's just enlarge our definition a little bit, and what I want to do is I want to say, we want approximate scalability. But now what notion of approximation we're going to do? Well, I'm just going to take, like, my distance to doubly stochastic. And what is the distance that I want? I'm just going to say, take my rows, subtract 1 over n, take my columns, subtract 1 over n, right? That's the distance to the vector, like all 1 over n. And I'm just going to take the L2 norm of this vector, right? So that would be my distance to doubly stochastic. It's how far my rows and columns are from being just the uniform. Does that make sense? Okay. And now I'm going to define the following. Like, the approximate scalability will be that A is approximately scalable if for all epsilon that you choose, there will be scalings, like I can scale the rows and the columns such that when I do this scaling here, the distance of this matrix to doubly stochastic is less than or equal to epsilon. And now with this definition, we include that 1, 1, 0, 1 example. Questions so far? Okay. So, okay, but this is just kind of a motivating problem, right? So you could say, okay, well, why do I care exactly just by doubly stochastic? I could have said, well, what if I have some target like row marginals, like those are the row sums, and I have target like column sums, right? So this, if you think of the matrix as like a probability distribution, right, like a joint distribution, I have what? My sums of the rows are going to be one marginal, and the sum of the columns are going to be another marginal, right? So if you're thinking in terms of probabilities, like, well, why do I want to just have like uniform marginals? What if I want to have like different marginals? And you can do that. You can definitely define, like, generalize this problem. Like, there's nothing special about the 1 over n, 1 over n, okay? So let's do that, right? So let me just kind of get the simplex here, which is the set of all, like, essentially probability distributions, right? And then, again, I'm just going to generalize my distance to doubly stochastic to the distance to the R and C marginals. And what is it going to be? It's just going to be, if I have these vectors R and C, which are my target marginals, it's just the distance of how far my row sums are from the specified marginal, and my column sums are from the specified marginals, okay? And again, I can generalize the matrix scaling problem that we had in the beginning to saying what? Well, now if my input is just a matrix, and now I don't care about the dimensions being the same as well, right? They can be different. I have a non-negative matrix, and I have my target row marginals and my target column marginals, and I have this epsilon parameter, which is my approximation parameter. Well, I want it to output yes if there are scalings, like row scalings and column scalings, that make this matrix here be very close to having marginals R and C, or no otherwise, right? And in case it's yes, I actually want the scalings. That will be important.
So is it true that if delta is less than epsilon, then the distance to a truly doubly stochastic matrix is also epsilon?
Sorry, say it again?
Is this the same thing as distance to the nearest doubly stochastic matrix?
Oh, like if this is the same as the distance of A to the nearest doubly stochastic matrix. So that's a very good question. And so, yeah, it will be.
Doubly stochastic is for the standard of
Yeah.
the distance to the set of doubly stochastic matrices, right?
Yeah, but I think there's
The distance to the closest doubly stochastic.
yes, it is related, and it will enter somewhere. But like or whatever factor you lose when you're trying to translate this to the other is something that is a little bit non-trivial. But yeah, the answer is yes. But I was just, yeah. If you care about like the precise, like you're saying, like when I change the entries of the matrix, what happens to the?
I know, but they're
Okay, they're related,
They're
definitely.
related.
Yes, definitely. Okay,
Is
yeah.
that also a version of this problem where you put a rank on a bound on the rank of your target? Instead of just being doubly stochastic, you just say it's at most whatever?
Well, the rank doesn't change because if you remember the other formulation that I was giving, like every time that I'm scaling my matrix, right? If I have my matrix A, I'm just multiplying on the left by something invertible, like, and on the right by something like invertible, right? So then the rank is always the same. Yeah. Okay, more questions? Yeah.
Can you reiterate for me the intuition for just marginals in this context?
Yeah, if you think of A like as a joint probability distribution, right? Like, and then if you sum the rows, you get the like row marginals, and then if you sum the columns, you get the column marginals. Like those are the two. Like there's two probability distributions, like on M and N, and then like, yeah, A is like a joint probability distribution that realizes those marginals, right?
Great, thank you.
Cool. Yeah, more questions? Great. So, okay, and then, okay, you asked a lot of questions about, okay, uniqueness and all that kind of stuff, but, right, and this is kind of two problems of interest here. What's the computational complexity of this problem, right? Like, so how long does it take? Like, how fast can I solve this problem? But if you remember, the first question that we had is like, if given a matrix, we want to know if it's epsilon approximate, like if it's approximately scalable. But this approximately scalable has like a for all epsilon. For any epsilon that you give me, I can get epsilon close to the target marginals. So I mean, my solution cannot be, oh, for every epsilon, run this algorithm, and then if you get it, you output yes, right? So we want something that will tell you yes or no without having to test for every epsilon. So, and in one way to resolve this is like, well, is there a particular epsilon naught, like a threshold, right? That's a function of A and your like target marginals, such that if the answer is yes for this particular epsilon naught, then is yes for any epsilon, right? So if we can prove that this epsilon naught exists, then we can say, okay, A is epsilon naught scalable if and only if it's approximately scalable, right? Does that make sense? So if we prove that such epsilon exists, then we can solve our approximate scalability question. Sounds good?
Are you going to assume like integer entries or something?
For now I won't, but you can.
Okay.
Yeah, you certainly can. And for the purpose of our algorithms, like, yeah, I'm always going to say that A has like rational entries, or like I clear denominators and my matrix has integer entries. And that will enter in the full complexity of my algorithm. Yeah, definitely. But you don't need to for today. Yeah, more questions?
I guess the reason I'm asking is if
Yeah.
it's like a real value matrix, I would think hoping for something like this would be unreasonable. But maybe that's not true.
Right, we'll see.
Okay.
Yeah. But that's a great question. Yeah, you should keep that, and then if we can discuss later on, like I have slides. Yeah. Great. Okay. So you asked a bunch of stuff about this problem, but not why this problem, right? Like, why would anybody care about this problem? Well, it turns out that like this problem is so cool that it appeared in like several areas of science. And Schrödinger was not even the first one. Apparently, there's someone that did stuff on this like on 1910s or something. Okay, but I don't know. Every time I give a talk like this, someone gives me another reference. So this list is growing. But anyway, so it appears already like in Schrödinger's bridge problem, like in 1931. Kruithof, like was a telephone engineer. He's like using this matrix scaling for telephone forecasting. And then it appears also in economics and accounting. Yeah. No clue because the paper's in German, so like maybe Peter will tell me. But it's definitely the title I know. That much German I know. That is a.
Is this the famous Schrödinger from physics?
No, definitely. I mean, why would I put a non-famous Schrödinger? I mean, I don't care about any other Schrödinger. I mean, sorry, maybe I care. Yeah, okay.
It's also written in German.
Yeah, but that's so famous that's translated, right? And yeah, so okay. Well, some people can tell me this if this is fake news, but I read this somewhere that it's also used as a preconditioning subroutine in numerical computations. And in 2013, like Couturi used this kind of scaling algorithm to actually in computational optimal transport, so you can actually do approximate, like regularized optimal transport, and this is very important for machine learning and computer graphics. And Lineal, Samorodinsky, Wigderson used this algorithm to give a deterministic approximation of permanence of non-negative matrices, and also to give a really cool algorithm for bipartite matching. And this is also used in extremal combinatorics for fractional Sylvester-Gallai configurations, and many more applications. Okay, so you can see that this problem is cool, right? So hopefully, I guess none of these like won Turing Award, baby Turing Awards, like Jim was saying yesterday, but well, Avi won a lot of stuff, so maybe we can say that. So won a lot more. Okay. So, anyways, but Okay, hopefully this motivates you without even awards, right? So,
Marco just wants some big career transfer.
oh yeah, I mean, this is very cool. Yeah, for sure. Yeah. So, okay. Now here's like even when people came up with this problem, right? Like independently, people came up with this problem independently. They also came up with this like really cool way of solving it, right? They didn't prove anything, but they just okay. Here's one algorithm, right? So okay, and now from now on, I'm just going to be in the case where my matrix A is a square matrix, and I'm going to go to the doubly stochastic setting, okay? Because I don't want things to get like ugly for no reason, more than they need to be, right? Like. Okay, so here's basic operations on a matrix B, right? I have a square matrix B, and here are my rows. Like this is my vector of rows. This is my vector of columns. Oh yeah, by the way, every time I write like diagonal of something, I mean, you just know that like diagonal of a vector x is just going to be the matrix like x1 up to xn, right? I hope nobody questioned my notation, but I just want to say it. So here's what we're going to do. So if my matrix B has this, like these row sums and these column sums, I'm just going to say, well, the process of row normalizing B will be what? I'm just going to take B, and I'm going to multiply it on the left, which means that I'm scaling the rows, by the inverse of these entries, right? And then I'm just kind of, there's this scalar factor here, just because I always want to scale by determinant 1 matrices. Because remember, I don't care if, remember, my notion of doubly stochastic was something that was norm independent, right? So if I multiply this by like a scalar, it doesn't change the fact that this matrix still has row normalized. Is it still row normalized? Does that make sense? That's why I'm just multiplying by these guys here. But for now, if you want to forget about it, like just kind of forget about these determinants being here and just say, okay, this row normalized, what is it doing? This ugly thing is just saying, I'm taking B, and I'm multiplying on the left, I'm normalizing it so that all the rows of B have the same sum. And column normalized just makes like this matrix here is a scaling of B where the columns have the same sum. That's all that I'm doing. Sounds good? Okay. So, all right, so here's the algorithm. Right now that I define, I can give you the algorithm. I give you a matrix, and I just want to know if it can be scaled to epsilon close to doubly stochastic. Well, I start by just column normalizing A, and then for some amount of time, I'm just going to like flip-flop between those two. I'm going to row normalize, column normalize, and then if for any time in between like 0 and like 2t plus 2, I have one matrix that gets epsilon close to doubly stochastic, then I output yes, otherwise I output no. So that was the algorithm that everyone kind of came up independently with, and people didn't analyze. It's not Sinkhorn because Kruithof already came up with it, so I don't want to give Kruithof. Yeah, and then before Sinkhorn, even Sinkhorn says already, I didn't come up with it. I'm just analyzing in his paper, right? So, but as math goes, I think people admit it. That's why I don't like it too. Yeah, people, yeah, everyone already had this algorithm. So, yeah, it's known as like RAS algorithm, like IPFP, whatever. So there's many names to it. No offense to Sinkhorn, but so. Okay, sounds good? So this algorithm is cool for everybody? Pretty simple? Okay, right? Extremely useful in practice, again, independently discovered by a bunch of people. And okay, but what's the question, right? If we want to decide whether A is approximately scalable, well, does this algorithm always work, right? And if it does, like what T and epsilon should we choose, right? And I mean, Sinkhorn has a lot of credit for it because he said when A only has positive entries, then he proves that this algorithm converges. Didn't give an analysis of how much it converges, but he proved that it converges, right? So, but apparently before Sinkhorn, someone already had proven that too, so like in the 40s. So again, like I don't want to be very divisive, right? So let's be united here, just learn. Okay, so okay, let's run through some examples of what Sinkhorn is doing. Right? So what is Sinkhorn doing? I'm doing the example here for you. Let's take that simple matrix A that we had before, like 1, 1, 0, 1. Okay, if I normalize, remember, my first step is always normalize the columns. So this guy is good, right? And then this guy becomes like half, half. And then I have to multiply by 1 over the square root of the determinant of my column. So it's just going to be some scalar, which I'm going to say this is going to be alpha 0. Okay? I'm just keeping track of these ones because they're easy, right? And now this matrix is column normalized, but it's not row normalized. So we need to keep going, right? So my A1 is going to be, again, some scalar. But now I'm just going to make like the row sums to be 1. And what are my row sums here? They're going to be like, well, this is going to be 3/2, right? So I have to divide by 3/2, so multiplying by 2/3. So this is 2/3, 1/3. And this becomes like 0, 1. Does that make sense? And then I multiply by something here. Then you just say, OK, this is some alpha 1, some scalar. Does that make sense? And then if I keep going, what happens? Notice that this guy here is always decreasing. It's like 1/2, 1/3, 1/4, 1/5, and so on, right? So in general, this guy is going to be like, if I'm at the 2nth iteration, this guy is going to be, I'm going to be column normalized. So this guy is always going to be 1, 0. And this guy is going to be 1 over 2n plus 2. And this is 1 minus 1 over 2n plus 2. OK? And if I look at the row normalized, again, this row is just like 0, 1. And this guy is going to be 1 over 2n plus 3 and 1 minus 1 over 2n plus 3. So you can see that this algorithm is actually converging in this example. Right? Does that make sense? But now I'm going to show you another example of it.
Is this determinant one thing?
It will come in later. That's why I'm putting it here now. But yeah. Like right now it looks like I don't. And OK. If I don't, my analysis changes, but then the generalization changes. So anyway, there's, yeah. OK. But yeah, you can kind of ignore the determinant one for now. OK. So now let's take this matrix here. Right? Let's try to run the algorithm on this matrix. OK. So I'm going to column normalize. So it's, again, going to be some alpha here. You can ignore those for now. OK. So this is going to be 1/3, 1/3, 1/3, then 1 and 1. Column normalized. Great. But now I messed up the rows. Right? And then, so when I try to correct the rows here, well, this sum here is like 7/3. So then I have to multiply by 1 over 7/3, which is 3/7. So 3/7, 3/7. And then this gets 1/7, and this is 1, 1. And then again, now I have to, whenever I column normalize, right, now I'm going to have, like, this sum is 15 over 7. So this becomes 1 over 15, 7 over 15, 7 over 15, 1, 1. Right? But notice now that, like, regardless of what I'm doing, like, this guy, this answer here is going to 0. But if this guy is epsilon and I'm row normalized, like, notice that these two are always the same. Right? So this is going to be 1 minus epsilon over 2, 1 minus epsilon over 2. Right? Which means that this column here is very far from having some 1, because this guy has some, like, well, this guy has some like 2 plus epsilon. This is like 1 minus epsilon over 2, 1 minus epsilon over 2, right? So this guy is very far from having like equal row sums or equal column sums, right? There's always like a factor of like 4 here, right? This is like roughly half, and this is roughly 2. This is roughly half. This is roughly 2. I don't seem to kind of escape this curse. Does that make sense? Yeah? Just by running this algorithm, right? Like I cannot get it closer. Questions? Yeah?
So you gave us a bunch of references for similar work. This has a little bit of the flavor of balancing for eigenvalue computation.
That's correct. So matrix scale. Oh, I forgot to say that, right? Because yeah, like probably you guys from this community like care about matrix balance. That's a good cousin of matrix scaling, right? And they're just cousins. Yeah, like everything that works for matrix scaling also works for matrix balance pretty much. Yeah. So matrix balancing is also very famous. Has a yeah. And we can do similar things to matrix balancing.
But is balancing the same problem with?
I think that's usually 2 norms of columns in rows.
I see. Okay.
Yeah, yeah. I mean, here I could have done everything again with like L2 norms as well. I just because the way that they present is L1. But yeah, matrix balancing you can do like the only thing that you do is like the difference. Also, you do like you multiply by x here and by this matrix inverse on the other side.
Ah, okay.
So and then like you want to balance like yeah, and then your matrix is symmetric and so on. So. And the row sums, the column sums are the same because the matrix is symmetric, and you're preserving that as you go. Right. So yeah, you can think about this as also for matrix balancing if you like, and everything works for matrix balancing as well. Okay? Great, but is everyone with me here that like we can't seem with this algorithm like we're not going to converge, right? Like this is not going to converge here, right? Great. Okay, and then now we have to ask our question, okay, are these the only cases, right? And if they're the only cases, like there's always, okay, a good case and the only bad case is the case that we saw, okay, how can we distinguish between them, right? Okay, so to do that, I want to look at the matrix scaling from a different perspective. So now I'm going to have a different version, okay? And then we're going to talk about why they're equivalent. So, and again, we're going to take like m equals to n again, so just square matrices and just doubly stochastic, okay? So here's another problem that I'm also calling matrix scaling, and you can question me why, right? So, which is a norm minimization problem. So here, I'm going to have my matrix A and a parameter epsilon. And what I want to do is I want to output yes if there are scalings such that, and again, like this division here is just saying, suppose that this matrix here over this guy is a determinant 1 matrix, and this one over this is a determinant 1 matrix, right? So I'm just pulling out the determinants here. And all I'm saying is that if I scale my matrix by diagonal matrices determinant 1, I want to know if the norm of this guy is going to be less than or equal to epsilon for whatever epsilon you want. And if you can find something, a very small norm, give me the scalings. Otherwise, I'll put no. You cannot scale below epsilon. You will never have a matrix of norm less than epsilon.
So this is L2 norm again?
No, this is all L1 norm. This norm here for now, for this talk, is going to be L1 norm. Okay? Sounds good?
Is there should be like a difference between the ones?
Sorry?
When column sums of A?
No, this is going to be just the norm of the whole matrix. The norm is just the sum of all entries here. Is the L1 norm. Yeah.
But this should be, can be done only if the determinant is 0. If you want to make it very small, it means the determinant of A is very small. Because the determinant doesn't change. We do this transformation, the determinant doesn't change.
Okay, the all ones matrix cannot be scaled to 0, right? But has determinant 0. So determinant is not the right answer. Okay, but we're going to see it.
But at least, okay.
But we're going to see what the right answer is. But definitely determinant is not
It is a
true.
necessary condition.
No, because remember, the all ones matrix is already double. Like you can't do anything there. The all ones matrix is already there, and the determinant is 0.
Yes, sorry, not but necessary condition. What you do is not sufficient. Necessary condition is a determinant of A.
Sure, but I want an equivalence, and it will be much nicer than that. So.
Can't you use an identity?
Okay.
No, because it is
So, okay. So now, here's the function that I'm going to use. Okay. So my function here is this is the norm of a matrix, right? When I scale by determinant 1, but this norm is looks a bit ugly. So I'm just going to take the log of this norm, and I'm going to call this function like f of a of the scaling xy, right? So, so this is just going to be like log of the norm of my matrix. Okay. So if I split it, it's just like the log of the norm of the matrix minus like this log of like the determinants that I'm paying, right? So now, okay, now I wanted to care about those determinants. Okay? Yeah.
Maybe I missed something. Like this thing you're showing is less than epsilon. We should be understanding that as a measure of being close to balanced.
Not yet.
Not yet. Okay.
Not yet. Yeah.
Different measure. Okay.
Yeah, it's just a different, right? It's a different problem.
Okay.
But I'm also calling matrix scaling. You're right. Like, why am I calling this matrix scaling, right? Like, why is this also making progress in the other problem?
Wait, can
Right?
I also ask you a question?
Yeah.
I just got lost. On the previous slide, when like that matrix,
Yeah.
was that an issue with the algorithm, or that was just like that matrix?
Oh, great. Yeah, of course. I was going to address this point later, but let's address this point. No. It's a great question. We can address this point now, right? This matrix, right? Well, is the algorithm wrong, right? I guess I was planning to address that later, but let's address that now. Is the algorithm wrong? And the claim is no. The algorithm is not wrong because this matrix here can never be scaled to anything close to double stochastic, right? And why is that? Well, because here's the thing, right? Like, if this matrix is close to double stochastic, let's say double stochastic is like row sums and column sums 1. This is going to be 1. This is going to be close to 1. This is going to be close to 1, which means that this row has to be norm close to 2. Right? But this guy has norm close to 1. So this number, like these numbers, again, right? So this guy is going to be 2, and these guys have to be 1 and 1. So this matrix can never be scaled to close to double stochastic, and this algorithm is not converging for that very good reason, right? So somehow this algorithm is working, right? We just don't know when to stop, right? But it is working. Very good, very good. More questions about the algorithm? Yeah.
So the difference between the second example and the first example is just you added on an extra, like the first example is layered within the second example in some sense, right?
The first example, not really. Okay, great. So let's talk about what is the difference between those two examples. I wanted to talk about this later, but let's talk about this now. Great, right? They kind of look the same because they have some zeros and ones, right? Like, okay, but what's the difference? Is the number of zeros and the number of ones. Like here, there's I'm going to call this guy like a small block of ones. And like, well, yeah. Huh? Small block of zeros. Okay. Thank you, yeah. Right? And on this one, the problem is that it has like a big block of zeros. And what I mean by small and big is when the sum of the dimensions, like 2 plus 2 is 4, which is bigger than the dimension of the matrix. Yeah? So that's what I'm going to call big. You have a block that's this big, that the sum of these dimensions here is bigger than the dimension of my matrix. Right? And in the first example, my block of zeros here, my biggest block of zeros has dimension 2, which is exactly the dimension of my matrix.
Okay, interesting.
Yeah. So this turns out to be very relevant, right? Like, what is the dimension of the biggest block of zeros that I can have inside? Okay, so that's why these two examples are different, because this guy has a small block of zeros, and this one has this giant block of zeros.
The permutation of the columns does not matter at all, right?
No, doesn't matter at all. Yeah. Okay. Sounds good so far? Okay, great. Okay, excellent. So, right. So is this the only thing? So maybe, okay, now that we discussed this, it's probably actually better discussed here anyway. So keep asking questions. That's great. Are these the only cases? Like, if I don't have this big block of zeros, my algorithm will converge somehow. And if I have this big block of zeros, I know already that I can never be close to double stochastic. So then my algorithm will not converge. Right? So are these the only cases? Right? Okay. And now I'm going to switch again to like my different problem, which is this norm minimization problem. And again, I had that function that is like the log of the norm, right? And okay, but now here's just an observation, right? So if B is a scaling of A by determinant 1 diagonal matrix, so if these matrices have determinant 1, this ugly term disappears, right? And this is exactly B. So f of A, when I scale by x and y, just becomes the same thing as f of B if I don't do anything, right? Like if I scale by the identity, I'm not doing anything, which is just the log of the norm of B. So that's why I'm calling this like norm minimization, because if I scale by things with determinant 1, I always get that I'm just getting the log of the norm. And I just want to minimize the log of the norm.
So, yeah, I was going to ask, why do you just insist on
I needed to motivate it, right? So I don't do things without motivation.
Later on it will be generalized.
Yeah.
And it will be consistent, otherwise there's a change in notation.
So I want to leave that mystery out there, but I think it's natural to everybody else, right? So it's for the other side of the program. So if everyone's okay on the other side, like everyone's happy or nobody's happy, or okay. So great. Okay, so now what do we want to compute? And I'm going to call this I'm going to call like this infimum of this function here, the infimum of the log norm. I'm going to call this like log capacity, okay? And we can talk about capacity later, but I'll defer that conversation for when Leonid is here, okay? So you can talk to Leonid about this. Okay, so we want to kind of compute this infimum. Okay, but what do we know how to do in life? Right? So, and okay, there's two questions here. Like, why are these two versions equivalent? I haven't answered that to you, right? And the other thing is like, okay, what is the only optimization that we know how to do in life? Convex optimization. Great. So it turns out, like, why are these two versions equivalent? Because of this convexity of this function. This function fa is actually convex. Okay? And, all right, but convexity just doesn't answer anything, right? Like, I want to show you why. Okay, so let's think of fa as a function from all the reals, like as a function from r to the n to r via composition with the exponential map. So what am I going to do? I'm going to take any vectors like u and v, I'm going to take their exponents. So this guy becomes now like positive entries, right? Positive entries, right? And now I can scale. I can scale by the diagonal where e to the u. Does that make sense? So this is like matrix with positive entries in the diagonal, matrix with positive entries in the diagonal. Does that make sense? So now I have that my norm function is the log norm of this function here. OK, great. And now I'm in the Euclidean setting, right? After this reparametrization, right? This is what people call it geometric programming, right? But like after I do this parametrization, if I consider this function as a function of u and v, right? I'm in an Euclidean space. Great. Everything is excellent. And now I can do the usual thing that we do like in undergrad calculus, like to prove that something's convex, right? I can take two derivatives and then check that they're always non-negative, yeah?
Maybe worth clarifying what e to the u as element was.
Sorry?
E to the u is performed element.
Oh yeah, e to the u is always element-wise, right? So if I have like e to the u1 up to un, yes, let me clarify that. It's just going to be like the e to the u1, e to the u2, e to the un. That's correct. Let me explain my notation here. Yeah. So, OK. And now if I do that, right, you can show that this is convex. But not only that, if we compute the gradient of this function. And again, how do we compute the gradient of this function? Well, remember, the gradient is the vector that when I take the inner product with the direction that I want to go to is exactly my directional derivative, correct? So that's the formula that I'm going to use to compute my gradient, right? And how do I do this? Well, if I take this derivative here, okay, that's not bad. I just get this, okay, and as an exercise for you to do this. So, but now let's collect who is multiplying by ui, right? Because I want to figure out who this vector is. So I need to figure out, okay, but this vector inner product with this is going to be equal to that. But who is multiplying by ui here? Well, the guy that's multiplying by ui, well, let's take everyone that's multiplying by ui on this side is just going to be what? It's going to be 1 over the norm of a times the sum. Well, if I only multiply by ui, the I has to be fixed. So it's just going to be like aij, j equals to 1 up to n. Correct? That's multiplying by ui. And then what else is multiplying by ui? Just 1 over n. So I have minus 1 over n. And this is the guy that's multiplying by ui. But what is this? This is exactly the norm of my ith row. And if I do the same thing for the columns, I will also get that my gradient actually is exactly the vector of my marginals minus the uniform marginal. Does that make sense? So what?
The sig coordinate is running gradient design.
Exactly. Exactly. Block coordinate gradient descent to be more precise. Right? Yes. So if you notice, this function is convex. And when you look at the gradient of this function, is exactly the distance of my rows and column vectors from being all 1 over n, correct? Which means that the norm of the gradient, and now like the L2 norm of the gradient, is exactly the distance to double stochastic. Right?
In this formula, the norm of the matrix A is adding up all entries, right?
Yeah, it's adding up all entries. Yeah, that's what I said from the beginning. Yeah,
Just
yeah.
to clarify.
No, it's very consistent. I double check, but yeah. So does that make sense? And now here's the thing. But if you remember, right, like this is a convex, like this function is convex. We're minimizing a convex function, right? But when is the minimum attained? When the gradient is 0, right? Which is the same thing. Minimizing this convex function is the same thing as minimizing its gradient. And that's why the two problems are equivalent, right? It's because not only my norm function, my log norm function is convex, but its gradient is my distance to double stochastic. So if I minimize the distance to double stochastic, I'm also minimizing my norm. Does that make sense? Yeah? And that answers the questions to Nikhil, like that I want to, okay, yes. So as I'm minimizing the distance to double stochastic, I am getting close to like a double stochastic matrix, right? Does that make sense? Sounds good? Okay. So, all right, so we can prove that f is convex. And again, so minimizing the norm of the gradient is equivalent to minimizing the log norm, and then the two formulations are equivalent. So now we're all happy with that, right? And again, right, as Chris was saying, okay, this algorithm 1, like this like scaling algorithm, right, is exactly block coordinate gradient descent, because what is that? I first optimize over the row variables, and I make my gradient 0 there. So I'm really minimizing over all the variable. And then I optimize over the column variable. So I keep changing back and forth, right? And I'm always making the gradient 0 in one block, and then making the gradient 0 in the other block, right? Because when I'm row stochastic, my gradient is 0 on the row variables. When I'm column stochastic, my gradient is 0 on the column variables. Does that make sense? Great. So this algorithm is gradient descent. So like, yes, okay, now we have hope that this thing is actually converging, doing the right thing, right? So great. And now, here are questions. Can we get like a tight quantitative connection, right? Like, because as Chris is saying, okay, if my input's a bit ugly, well, how long would I have to run my algorithm, right? And can we prove convergence of this algorithm 1, right? Okay, so here's some observations we'll need to prove convergence, right? So if my log capacity is minus infinity, right, is if and only if I can scale A arbitrarily close to 0. Because remember, log capacity is the infimum of the log norm. So maybe let me just leave it here. Like what I was saying before is that my definition of log capacity of A was equal to the infimum over all the scalings like xy of the function like fa xy, but this function is the log norm of the scaled, right? So if I can get arbitrarily close to 0, my norm gets close to 0, which means that the log goes to minus infinity, right? So, okay, more questions? Yeah?
Ask a silly question. Is FA convex in X and Y or in U and V?
It's convex in U and V. Yeah. So, and okay. So, and if log capacity is like bounded away from minus infinity, so if it's finite, then I know that the gradient cannot be large all the time. Right? So, okay, and now let's talk about this invariant property of the scaling action. So scaling action is a very special action because it has this invariant property. And what is the invariant property, right? So let's say that B is a scaling of A. And for now, let's just say that this matrix like X and Y, they have determinant 1, just so I don't deal with these guys. Okay? What I want to prove is that for any permutation, if I look at the product of these entries, like bi sigma I, this is going to be equal to the product of the entries ai sigma I, like equal, right? And how can we see that? Well, what is the product of bi sigma I? Well, this is a scaling of A, correct? So this is the same as the product of xi, b or ai sigma I, yi, correct? Sorry, y of sigma I. My bad. Thank you. You're paying attention. That's great. Watch me like a hawk, right? Okay, and this is equal to like product of xi, product of y sigma I, but sigma is a permutation, so I'm just going to say that this is product of yi times product of ai sigma I. But remember, I was saying x and y, like these matrices have determinant 1 already, just so that I can get rid of these, right? Then what happens? Well, this is the determinant of the diagonal. So this is 1 and this is 1, right? So for any permutation, I get that the permutation is an invariant when I multiply on the left and the right by these matrices. Does that make sense? Okay, and we're going to use that, okay? So, and now here's the thing. What does this invariant property tells us? Well, first of all, let's look at the support of my matrix A. Right? What's the support? Is the entries that are non-zero. Right? So multiplying on the left and on the right, like by diagonals, doesn't change my support. Correct? Because I'm just scaling every entry. Right? There's no interaction between entries. So the support never changes. Now, if the support of A contains a permutation, then no matter what scaling I do, no matter what scaling I'm doing here, this quantity will never change, which means that my matrix cannot get arbitrarily close to 0. right? Because if it was getting to arbitrarily close to 0, all these guys had to be really close to 0. But the product doesn't change. Does that make sense? So if the support of A has a permutation, I will not be able to get as close to 0 as I want, which means that my log capacity is finite. Correct? Does that make sense? And now, well, if you remember Hall's theorem, right? So we can think of the support of A. We can think of the support of A as a bipartite graph, right? So I can just say here, for example, let's look at our favorite example, like 1, 1, 1. So if this is my matrix A, I can say, well, this is the adjacency, like the support is the adjacency matrix of a bipartite graph. I can say this is vertex like 1, 2, 3, A, B, C. So 1, 2, 3, A, B, C. And then here, well, what happens? 1 is connected to A, B, and C. Well, 2 is connected only to A. 3 is connected to A. Correct? Now, this guy has a big block of zeros. Hall's theorem tells us what? Well, this guy has no perfect matching. But what is the perfect matching in this graph? It's just a function that is injective from here to here, which is a permutation. Correct? So now we know, OK, hey, if the support of my matrix has a big block of zeros, then in any permutation, this product here for my matrix is equal to 0. Right? Because I'm not supported on any permutation.
So what's the actual statement of Hall's theorem?
Right. So, well, bipartite, well, is essentially this.
What's a big block of zeros?
Big block of zeros just means that if this is like I and this is j, I plus j is bigger than or equal to n plus 1. N is the dimension of your matrix. OK? Yeah?
So
What's the connection to the log? Okay, if the log cap's negative infinity, your first problem means it's scalable? Or no, it's the other way. What's the connection between the value of the log cap and whether or not it's scalable in the first definition?
Right. So, OK. So if you remember, like, if my log capacity here is finite, right, my infimum, I can go like to my infimum. Let's say
right,
that
so
I can
have a zero gradient.
Exactly. I have the zero gradient, which means that I'm scalable to doubly stochastic, right? But yeah, if I can never get to like the minimum point, right, in this case, then I'm not scalable. Exactly. Exactly. Sorry. Yeah.
Maybe I'll ask you later.
Sure. OK. So, all right. So now we know, like, OK, so we have this invariant here, right? So if my matrix has support in some permutation, I cannot drive it to 0, which means that the support has like a, if I consider the support as like a bipartite graph, right? Like this bipartite graph has a perfect matching. And that's the connection from perfect matching to this problem, right? But if not, then A has to be this giant, has to have this giant block of zeros. And we already showed, right, that if A has a giant block of zeros, I can never scale to close to doubly stochastic. So this is already a proof that, oh, OK, so that's good, right? So I know that now if A is supported on a permutation, then I know that this is going to happen. Because my norm cannot get arbitrarily close to 0. It's bounded away from 0. Right? But if I have a big block of zeros, right, then I know I'll never be able to, like, my gradient is never 0, which means like I can always like keep going further and further, which means I can get close to 0. Does that make sense? OK. So now, OK, so we recap our algorithm, right? So I'm doing this block coordinate gradient descent. And here's the thing, again. Well, we already discussed this, right? So if A has this big block of zeros, and what does it mean big? It means that if these are the dimensions I and j, I plus j is bigger than n, right? Then what I'm saying is that, remember, we said that we can never get close to doubly stochastic, correct? But actually, how far are we from doubly stochastic? I claim that the distance to doubly stochastic is greater or equal than 1 over n squared. OK? And this is the proof here. OK, so, and what is the proof? It's exactly the same proof that we did before. Right? So I'm saying if I plus j is bigger than n, then I know that j is greater or equal than n plus 1 minus n. Which means that, OK, if this matrix already is column normalized, then this guy sums to 1 over n, 1 over n, 1 over n, 1 over n. But the thing is that the sum of these guys here is less than or equal than the sum of these rows. Because these rows contain the sum of these rows contain all of this block. Correct? So the sum of these rows, they are greater or equal than j over n, right? But then j is greater or equal than n minus 1, n plus 1 minus I, right? Which means that the maximum of this guy is bigger than this over n minus I. And then I get my distance to double stochastic. Does that make sense? That's the proof. So I'm kind of this far away. And now we get our epsilon. So let's just set epsilon to be 1 over epsilon, 1 over n squared. Because I know if I have this big block of zeros, my gradient will never be smaller than 1 over n squared. Right? The norm of my gradient. Does that make sense? So that's my epsilon 0 that I'm going to set. Does that make sense?
Yes, you actually didn't require integer. It's just
No.
a weird phenomenon in this problem.
Yeah, crazy, no? It's cool.
You
Well-
required like integer for the row and column sums. Like if you had general R and C, it would become.
Yeah, general.
sure.
Yeah.
Yeah.
The magic, the integer. Yeah, the integer, as Akshay is saying, it's like okay, it comes from the R and C marginals. Like,
Yeah. But
definitely, if you change the marginals, then it can get pretty bad. Okay, and there's and the entries of A enter somewhere else as well.
Does this complete a full argument that epsilon being 1 by n squared is the right choice in the worst case for like a worst case guarantee?
Yeah, for double stochastic, yes. This
Okay.
completes the argument. Yes.
Okay, cool.
Yeah. Okay. So far, so good. Okay. And now remember, like this A tau here, right? Like every time that I'm scaling, remember, that's why I did the scaling by diagonal determinant 1. Now I need you to care about it, Nikhil. Okay? So, A tau is the scaling of A by diagonal determinant 1 matrices, which means that if I have like A tau is just this scaling here, then remember, I'm going to call this function F tau because it's just going to be what? It's just going to be the log of the norm of my matrix. Right? Just by that same remark that I told you guys early on. Right? So if I scale by determinant 1 matrices, then the value of my function is just the log of the norm of my scaled matrix. Right? So, okay. And now, what can we do? Well, now I know that the difference here between my iterations is just what? Is the difference between the logs of the norms. Correct? Okay. And now, well, what do I need to do? What I need to do is the following. So I need this notion, I need this kind of quantitative version of the AMGM just to make sure I'm making progress at every step. And what is the quantitative version? Well, you know the AMGM, right? So, okay, if I take the arithmetic mean is greater or equal than the geometric mean, correct? But now, and what is the equality case? Is when all the entries are the same. But I mean, this is not that great. What if I'm a little bit far away from having all the entries being equal? Can I prove a stronger bound? And this is what this inequality is doing, right? So if I have my numbers here, like positive numbers, such that they sum up to n, but now they're like, that's their distance from being all equal, right? That's the L2 norm squared, kind of, if it's alpha. Then what I'm claiming to you is that the product of alpha I is less than or equal than exponential of minus alpha over 6, if alpha is less than 1, or just exponential minus 1 over 6. Okay, that's pretty easy to prove. Easy calculus exercise. So, okay. And, okay, so what are we going to prove? So with this inequality, you can say if the distance to double stochastic of my matrix, of my scaling, is greater or equal than 1 over n, what I'm saying is that, remember that constant that I'm paying every time I'm scaling? That constant is exactly this, right? So I can use the AMGM to prove that if this distance to double stochastic is large, then this product here is less than or equal than exponential of minus 1 over 6n squared. So every time, if the gradient of this matrix here, the distance double stochastic is large, my next scaling is decreasing the norm by this multiplicative factor, which means that the distance between my iterations here is going to be, again, the log of this quantity, which is minus 1 over 6n cubed. Does that make sense? So now, if at every step, I'm far from being double stochastic, my log norm is decreasing by this amount, right? But then I have like, by telescoping, right? So if my gradient is always large, then I know that ft is less than or equal than f0 minus t times this quantity. But what is f0? F0 is just the log of my original matrix, the norm of my original matrix, right? So now, I have that my norm, the log of my norm is less than or equal than log a minus this. And now let's use the invariant to give a lower bound on this norm, how far I am from 0, right? So if the support of A has a permutation sigma, remember, I'm just scaling by determinant 1 matrices, right? So the norm of A tau to the n is greater or equal than the product of just the entries like AI sigma I of that matrix A tau, right? Because each of these guys is lower bounded, is a lower bound to this quantity. Does that make sense? But now this guy, remember, by the invariant property, this is a scaling of my original matrix by determinant 1. So this product is equal to this one. But this guy is less than or equal, is greater or equal to what? To the minimum entry, the minimum non-zero entry of my matrix A to the power n. Does that make sense? That's it. And now I know that if the support of A has a permutation sigma, I know that the norm of this guy here is always greater or equal than the smallest entry of my matrix. That's where it is another place where it enters the complexity. Does that make sense? So in particular, I know that F tau, if the support of A has a permutation, I know that my log norm can never be greater or equal than the log of the minimum entry of my matrix, right? And therefore, if we set T to be like 6n cubed times log of norm of A over the least entry of A, we're done, right? We're able to distinguish, like either we find a gradient that's small, or if the gradient is always large, I can say, okay, then this is going to go to 0. Does that make sense? Okay, so I have 3 minutes, I guess, right? Great. Wow, guys. Okay, recap.
About that before you recap.
Yeah, sure.
So, like, when you realized you could essentially earn gradient descent on this normalization problem, you didn't have to use like alternating gradient descent with like some fixed step size, which is what the scaling algorithm is doing.
Right.
You could have plugged this into like black box gradient descent analysis for convex functions.
Yeah, yeah.
And what is the reason to do it custom? Like that you would get a worse polynomial on n or something?
So, sorry, say it again, the last sentence?
If you do that, what will you get? Will you also get an n cubed time algorithm?
Well, okay, there's many ways to optimize this algorithm. So I'm just doing this one. Why did I do this one? One, because it's simple. Everybody does it, and it's really cool.
Okay.
So then they will be interested. But if I change, like, oh, here's gradient descent, someone's like, an economist, like, oh, now I have to learn gradient descent. It's like, okay, whatever, right? That's it. But you can also do it, and you get better bounds, and then you can even do better things. You can do second order methods. You can do, yeah, you can do whatever you now, like, kind of. Yeah, all hell breaks loose. Now you can do whatever you want. Once you know that this is convex optimization, you can get all those guys that do convex optimization, and then they can go to town on this.
Okay.
Right.
Well, if you just do black box convex optimization, you need Lipschitz gradient for that, right?
Yeah, I guess you'd have to argue something like that.
No, well, a priori, but yeah.
Forget it.
Leading up to the second talk, great, yeah. So awesome, I love it. Okay, recap now or? Okay, great. So what did we do, right? So we proved that like a non-negative matrix here can be approximately scalable to doubly stochastic if and only if like its support contains a permutation, right? So if and only if the support, like if you look at it as a graph, it has a...
Doesn't, right?
Huh?
Doesn't?
No, it can be approximately scalable to doubly stochastic if and only if its support contains a permutation.
It's not scaled to 0, it's scaled to doubly stochastic.
Yeah, it's scaled to doubly stochastic, not to 0.
Okay.
Yeah. Sorry, yeah, those are the two problems. Yes. So, okay. And what did we do for the analysis here, right? So, well, we used these two different formulations, right? Like there's a norm minimization formulation, and there's that scaling like formulation. And we proved that, okay, because of convex duality, these two forms are equivalent. And then we analyzed this norm minimization problem by using what? Well, we used the polynomial invariant, like this permutation polynomial that we have, which was an invariant to give a lower bound on the minimum of this log norm. And then we're able to prove that our algorithm will converge. Does that make sense? So convex optimization together with this polynomial invariant, we win. Right? So that's what we did. And again, yeah, the log norm function is convex under this proper parametrization here, right? As was asked. And again, and we saw that the gradient of the log norm is exactly the distance to this double stochastic. Okay, all of this can be generalized to like general margins, but I won't talk about it later. I can talk about it offline. And again, and once we saw, again, alternative minimization is block coordinate gradient descent, we knew that this is going to work. This has to work, right? So, okay, and in the next lecture now, we're going to see like a vast generalization of this to many other problems that you think might look very different. Okay, so that's it for me. Oh, yes, that's it for me.
Okay. More questions?
So I have a few remarks. Number one, we know like in the 70s, we were all sort of working on this problem on simple algorithms. Now you say that this German guy, whatever, or published this algorithm before. I never heard of it, but that's fine. So, but another, let's say, remark that that the fact that alternative minimization is uniformly descent, this was known before. Of course,
Yeah, I'm not saying anything here is new. I mean, I even Sinkhorn already knew that was not new. Sinkhorn before the 70s already knew that it was not new. So.
But your result is very nice because you made a quiz which is not classical, and I saw it first time. Okay.
Yeah.
Does this give any bound on the size of the diagonal scaling in terms of some feature equation later?
Great. Yes. Yes. But we can talk about it later. Yeah.
Are there any sufficient conditions for when there's like an exact scaling to doubly stochastic?
When there is an exact scaling. Yeah, we can. There's a couple of things that we can talk about in terms of exact condition. One of them that, like, let's say the easiest one that you can say is that if your function, look at that, we know that this function is convex. If it's strongly convex, you're good to go. So, and I guess that guy can say a lot more.
There's just a very simple combinatorial condition.
Yeah.
If you go back to that graph, is that every edge is contained in a permutation.
Yeah.
Every edge is contained in a
Oh yeah, true. Yeah.
The
Exactly.
question is, you want the exact when it's exactly doubly stochastic? This is well known. If and only if it's a linear problem. If and only if you can construct a doubly stochastic matrix which has the same zero pattern. Okay, or it is So that's the condition.
Okay, thank you.
Yeah, I guess the simplest one is the one that actually says, just look, it's the same, it's exactly the same thing. And again, this is also vastly generalizable. Yeah, so. Sorry, yeah.
If I want to go beyond the doubly stochastic to the marginal,
Yeah.
does it change what kind of graph structure I need to look out for?
Yeah, you do, because it's related to like what Shmuel was saying about the linear programming condition, which changes a little bit, and what actually was mentioning as well. Like, let's say that R and C is rational. If they're both rational, then you can construct like a different matrix from this, where scaling to RC on this matrix is equivalent to scaling to double stochastic on a bigger matrix, and then you can use that condition that Akshay was mentioning. But if it's not rational, if your RC are not rational, I don't know why you would do that, but if they're not, like, it's okay, because you just have to solve a linear program and say, okay, is this linear program, if it has a solution or not, it tells you whether you can scale or not. So
cool. I can maybe motivate the linear program you mentioned.
Yeah.
So when we scale this matrix, at the end, if you get R and C, you can think of that as an RC flow on this bipartite graph. Right? It's like sending R in and taking C out. Right?
Okay.
So at least something's got to exist with the same support. Right?
Okay.
If we're scaling, we're not changing the support. That's an if and only if. That's the magic of it. It's exactly captures it.
Okay.
yeah.
Cool.
Yeah, very smart.
Yeah.
Okay, well, thanks again. So you go ahead.
Hot mic here. Mic still on a hot mic? Or? I want to get caught on a hot mic. So. Yeah.
How do I remove this?